Hello everyone, welcome to the session of Zero Knowledge. My name is Binyi Chen and I'll be the chair of the session. In this session we have 3 talks, and the first talk is about ZK-friendly hash function that employs an S-box that uses power residues. This is joint work by Mincho Son and his colleagues, and Mincho will give the talk.
Okay, thank you for the introduction. I'm Binyi Chen from KAIST, and is glad to introduce my paper Polo, a GK-friendly hash function based on S-boxes using power residues in here at Eurocrypt. This work is a joint work with Jin-Chul Ha, Sung-Ha Hwang, Joyoung Lee, and Seung-Min Park. As a first presenter in this GK section, I believe that I deserve to introduce what GKP is. GKP is a two-party protocol that allows the prover to convince their knowledge of something without revealing itself. It means that zero knowledge. And important, for one example, prover can prove their knowledge of input X, which satisfies SHA-256X equals 0 without revealing X itself. In theory, every statement can be proven by prover, but the problem is some operations are highly inefficient in GKP. For instance, compare and bit operations such as AND and XOR are very simple operations in CPU computation settings, but it is very inefficient in GKP. This is because common GKP supports only addition and multiplication in FP. And I want to note that in our case, our hash function targeted Plonk, so our prime field is 256-bit prime field. And one interesting example is constraints of XORing two 8-bit integers required 49 gates in total. This is a bit huge. So, although hash functions are commonly used in GKP, the problem is standardized hash functions such as SHA-2 and SHA-3 are inefficient in GKP because they consist of many bit operations. So this led to the invention of GK-friendly hash functions. GK-friendly hash functions consist of addition and multiplications on field FP. I draw some MIMC example in here. In MIMC, their S-box is X cube, which is represented in multiplication, and linear layers is just simply adding constant in FP. So this design rationale gives huge significant benefits in GKP. But the problem is their structure is algebraically simple. What it means that they are often vulnerable in algebraic attacks. Many designers propose their structures, and even they put their best effort, many of them were broken by algebraic attacks. You can check that 4 out of 7 were broken by algebraic attacks. And one more operation that GKP allows is lookup argument. Using lookup argument, a prover can demonstrate a witness E belongs to a public table T. And lookup operations allow GK unfriendly operations to be handled more efficiently. As we checked in previous example, XOR of two 8-bit integers requires 49 gates if lookup is not allowed. But if lookup argument is supported by proof GKP, then it requires 5 gates instead of 49 gates. So recently, some recent proof system allows lookup argument. And our hash function Polo mainly focuses on PlonkUp, which is an extension of Plonk. And in PlonkUp, addition and multiplication FP is natively supported by Plonk, and also table lookup operation is supported. And in PlonkUp, the prover's complexity is proportional to number of gates and table size. And we can assume that table size is fixed constant. So our efficiency metric is the total number of gates in Plonk up, and which refers to Plonk gates. Okay. Our motivation is starting from the other GK lookup-based GK-friendly hash function, reinforced concrete. Reinforced concrete is the first hash function utilizes lookup table in their structure, and their strategy is similar to examples on XOR. The input X is decomposed into base of 1024, X1 to Xn, and they are fed to the underlying X box using lookup table. And since this table lookup is treated as a high algebraic degree, so it is believed that it could give a resistance against algebraic attacks. But one drawback in reinforced concrete is their high costs during composition and decomposition. What it means that reinforced concrete consists of 3 layers, and among them, linear layer and nonlinear layer requires only 5 and 8 gates, which is a bit small. But the problem is, table lookup layer requires 282 gates. It's seriously a lot. So reinforced concrete designer decide to put only 1 layer on their hash function in the mid. You can check that in the middle of here. And although only 1 layer out of 15 layers use table lookup layer, it accounts 75 of Plonk gates. So we inspire that reducing the cost of applying a lookup table, and rather than applying it only 1 layer, applying it over multiple rounds can enhance security and efficiency. This is our starting point. So our contribution is we propose PoloColo, which is abbreviation of power residue for lower cost table lookup. This is a new lookup-based GK-friendly hash function. Our 2 building blocks are newly proposed. The first S box is constructed using the power residue method, and this allows to apply a lookup table with less cost. And second one is we propose a new MDS matrix, which is moderately efficient in Plonk. As a result, PoloColo requires fewer Plonk gates compared to the state-of-the-art GK-friendly hash functions, and we will revisit these results at last. So, how to apply lookup table to an input X? To apply a lookup table to an input X, then X should be mapped to table input, and what it means that the size of the range of F should be limited, and this size can be varied, but we choose about 1024. And a simplest example is fx equals remainder of x divided by 1024. This is used in reinforced concrete, and our approach is a bit different. When a multiplicative group, the field FP can be represented as a multiplicative cyclic group with order p-1, and in this case, we can represent input x as a g to the e for some exponent e. And moreover, when we choose an integer m, which is a divisor of p-1, we can uniquely represent e equals qm plus r for some quotient q and remainder r. And in here, r is determined 0 to m-1. So for each x, the remainder r only has m different values. So fx equals r can be used to applying table lookup. But the problem is, to compute fx equals r directly, we should solve discrete logarithm problem in FP, which seems inefficient. It could be possible, but it could be inefficient. So our solution is, rather than compute fx equals r directly, we set fx equals x to the p minus 1 divided by m, and this f is determined by r. You can check the examples on table. The rightmost column is fx, and it is determined by r. And this fx is called m's power residue of x. So this m's power residue goes through the table, and our new S box is defined as x inverse times table of m's power residue. You might be wondering how this S box comes from. So let's take a look into how this S box derived. This is we want to build a new S box from power residue, and this is a starting point. We start with identity function, and the types of color like blue, red, or green is determined by Q, and the opacity is determined by R, and this identity function is changed into like this, as term R is changed to sigma R, where sigma is a permutation on 0 to m minus 1. It means that the elements having same Q are mixed. After that, we change the term Qm to minus Qm. This changes a batch of elements which having same color, mix them the batch of the colors. At last, we add a plus Rm term. It mixes the element having same opacity, and as a result, you can see that the output of S box becomes more colorful. What it means that S box becomes more mixed. So this S box is our S box. Sx equals g times g to the minus qm plus rm plus sigma r. And although any m which is a divisor of p minus 1 is well defined on this S box, we set m as a 2 to the 5 to the 10. And sigma is basically randomly chosen in the nothing on my sleeve manner, but we reject some weak permutation. Weak permutation means that the table constructed from this sigma is algebraically simple. That might be vulnerable to algebraic attack. But if we choose sigma randomly, almost all of them are not weak. So when we manipulate this equation, we can earn Sx equals x inverse times table of m's power residue. And also, this S box should be represented as a Planck constraint. To represent a Planck constraint, we introduced 4 new witnesses, W1 to W4, and their value is G to the Q, G to the R, blah blah, and their constraints have 4 equations. And all in all, we need log m plus 4 gates in total. If n is 1024, it requires only 14 gates to apply lookup table to an element x. And also, our linear layer is optimized for Planck. In general, linear layers in GK-friendly hash functions are defined by the constant vector c and the matrix. The constant c is usually randomly chosen, and the matrix M should be MDS matrix to provide a stronger security against statistical attacks. And at first, in general, multiplying our matrix M requires t times t minus 1 add gates. This is an example for t equals 3, and you can check that 1, 2, 3, 4, 5, and 6 gates to compute matrix multiplication. But depending on matrix, this can be done efficiently. You can check that in below example, only 5 gates are required instead of 6. So when t equals 3 and 4, there are known results, and we found a new matrix for t equals 5 to 8. The approach is simple. It is a heuristic approach. That is, we start with witness x1 to x5, then we just choose 2 random witnesses, and also linear coefficients are randomly chosen. Then we add them, and so on. When we generate enough witnesses, then check that whether the metrics derived by the last T matrices are MDS. And this is an example for T equals 5 used in Polo Colo. This requires 13 addition gates, which is better than 20 gates, which is in naive way. So our Polo Colo, our linear layer provides stronger security without degrading their efficiency, highly degrading their efficiency. Okay, then all building blocks are provided. So we can just design a Polo Colo permutation using SPN structure as a linear layer and hash boxes are provided. Then this permutation is converted to hash function using sponge construction. This is a well-known structure in most of GK-friendly hash function uses this approach. And yeah, we also do security analysis. Time is running out, so I cannot go in detail, but we include an additional 1 round security margin, and also algebraic attack is the complexity of algebraic attack is at least 2 to the 160, while our security parameter is 128. So our performance our table is like this. So you can check that our Polo Colo is required fewer Plonk gates compared to the other GK-friendly hash functions. And I noticed that about 2 hours ago, the attacks on Anemone was proposed in here Eurocrypt. So anyway, and Griffin and Arion are vulnerable. Their original specification is vulnerable and not fixed. So we compared with it no security margin variants of Polo Colo. So this is our conclusion. We present a new GK-friendly hash function Polo Colo based on the power residue method. And so as a conclusion, Polo Colo achieves the smallest Plonk cost to existing schemes in this category. And we believe that this power residue method and new linear layer can be applied to other GK-friendly hash functions. And I believe that third-party analysis is most essential because this power residue method is newly introduced, and the efficient system, how to build a system application can be help to understand security of Polo Colo accurately. Okay, this is the end of my presentation. Thank you.
Yeah, please go ahead.
Hey, thanks for the talk. I have a few questions. One question is, what happens when you use this in R1CS? Is it better than anything?
Generally R1CS and AIR can be also comparable cost, but as far as I know, I couldn't find any proof system that support lookup argument in R1CS. So I just use Plonk.
And so this is a broader question about ZK-friendly hash functions. Out of everything that you kind of showed, which one do you think is currently the most trustworthy?
If someone asked me to, is it okay to use Polo Colo in our structure, then I believe that it is not recommended because it should be highly peer-reviewed. And I believe that Poseidon is the most better one because Ethereum Foundation works on it, and there's initiative something. So I think time helps to find a
Poseidon
new standard.
1, not 2. Poseidon 1.
2 might be better.
Okay.
Thank you.
Yes, so it seems that you claim that your cipher is not broken with the same attack as all the other ciphers. First, because you added just 1 round, so it's 3 rounds versus 4 rounds. Secondly, you add this small permutation, sigma. So the question is, are there any implementation constraints on this permutation? It can be just a random permutation. And second question, how many size in bits it has in practice according to you? And do you use an APN, or do you currently think that should be using just a random permutation without any constraint?
Sorry, I'm missing. So could you say again for the first question?
Yeah, so it seems that you claim that your cipher is not broken by the same attack which breaks all the other, just for two reasons. The first reason is that it has 4 rounds instead of 3. Okay, this seems to be the claim. And then because you use this small size permutation, which seems to be added compared to other ciphers.
Yes.
Okay, so do you claim that this makes your cipher secure, this delta, or is there any other delta which makes you think that your cipher is more secure than all the other ciphers which are broken?
I cannot say our cipher is most secure, but at least I can argue is that I try to conduct all of existing attacks, and it doesn't work for ours. Yeah, that's all.
Okay. Second question is: do you have any constraint on the choice of permutation in terms of the cost or implementation or security, or at this moment, no, not at all?
Chosen for what?
For this small permutation.
Sigma?
Yes, sigma.
Okay, let's check.
Yes.
I have it at that on appendix. Yeah.
Maybe you can take this offline because
okay.
we're running out of time. Yeah. Yeah, let's thank the speaker again. Okay, the second talk is Zero Knowledge, RAM, doubly efficient, and black box. This is joint work by Yuval Shai, Rafael Ostrowski, and Akash Shai, and Akash will give the talk.
Hi, thank you for the introduction. So let me first discuss the notion of arguments for RAM programs. So in this, prover commits to a huge database of size X in the offline phase. Then later in the online phase, it wants to prove execution of multiple statements on this database X. For instance, in the ith instance of the online phase, it wants to prove a statement corresponding to NP relation Ri, which is verifiable by a RAM program which runs in time t, which is sublinear in n. That is, in its entire lifetime, Ri happens to access only a few bits of the database X. Then, given the witness Wi, prover will interact with verifier and try to convince it that relation Ri, when given RAM access to database X, along with witness Wi, outputs accept. Now, this is repeated for many online phases, and we have the soundness and completeness guarantee that with respect to a database X, the completeness and soundness should hold. So what I mean is that if prover is proving multiple statements, then you should be able to effectively extract out a database X that can be shown to be consistent with all the proven statements. Now, in our work in Crypto 23, we constructed RGRAM construction with the following salient features. That is, the communication cost was polylog, the online prover time was sublinear, and our construction made only black box use of collision-resistant hashing. In this work, we consider the notion of RGRAM with the zero-knowledge property. That is, in this interaction, verifier should learn no information about the underlying database and the witness. So the goal of our work is to come up with a ZK-RAM construction with the same features with which we constructed RGRAM in our previous work. Now, satisfying any two of the three goals is known. That is, there are works which construct concretely efficient ZK RAM, but then they suffer from linear communication overhead, where the communication is the size of the runtime of the RAM program. Then there are works which try to reduce the verifier's overhead as much as possible, but the online prover time is quasi-linear in the size of the database. Then there are some constructions which make non-black box use of the underlying cryptographic assumption, and there are works on zero knowledge for data structures, and there are works that build up on IVC. Finally, there are works on lookup arguments which can be used to construct ZK-RAM. However, these constructions make use of bilinear maps, and they required a structured reference string whose size scales with the size of the database that has been committed. In this work, we designed the first ZK-RAM construction that satisfies all the three goals. More precisely, our ZK-RAM construction makes use of collision-resistant hash function only in a black box way, and the online prover time is quadratic in the runtime of the RAM program, and verifier is polylog, and our offline prover time is quasi-linear in the size of the database. And as a bonus feature, our construction also supports database updatability. That is, we can efficiently prove execution of RAM programs that update the state of the underlying database. Now, this is the outline of our talk. I am first going to talk about what PCPPs and projection codes are. Then I'll give you a high-level overview of our previous work's RGRAM construction using projection codes. Then we'll see challenges in extending this idea to ZK RAM. And this gives a way for us to introduce the notion of our new primitive, which we call locally updatable projection codes. And we'll see how locally updatable projection codes will help us to obtain a ZK RAM construction. So now PCPPs are standard in literature. What a prover does is that it computes an encoding of the input X, and verifier is given Oracle access to this encoding. Along with that, prover computes a proof pi for the NP statement R on X, W outputs accept, and verifier is given to Oracle access to this proof as well. Then the verifier is going to make polylog many queries to the input encoding and the proof pi. And we now know that there are even PCPPs where the prover time is quasi-linear in the proof statement. So let me define the notion of projection codes. This is from our previous work. It comprises of 3 algorithms: encoding, projection, and decoding. Given a message X, this is the database, you get the code word X of length capital N. Then given a sequence of message coordinates, the projection algorithm will output a sequence of code word coordinates, such that when you apply decoding on a code word Y, it outputs a message Y, and the projected code word should be robust, in the sense that if Y is delta close to the projected code word, then the decoding algorithm should output the projected message. Now, let us see how RGRAM construction worked in our previous paper. So here, in the offline phase, the prover will first compute a projection encoding and then commit to this encoding in the offline phase. Then in the online phase, for a NP relation R, it will determine the set of bits that are accessed in the database. Then it's going to perform a projection of this message and obtain the projected code word. And finally, it's going to generate a PCPP proof with respect to this encoding. So now, the nice feature with projection codes is that we do not need to separately prove that the encoding that we used for the PCPP is consistent to what we had committed in the offline phase. This is because the bits of the projected code word happens to be the bits that were committed in the offline phase in the global code word. So then verifier can simply verify the PCPP relation and convince itself that prover had computed correctly. There are some details that are missed, but this was just to give you an overview of how our previous construction worked. Now, the main issue in extending this construction is the input and access pattern leakage in our previous work's RGRAM construction. That is, the verifier was able to deduce the bits of the database X from the queries to the projected code word. Along with that, verifier is implicitly aware of the projected code word's message coordinates. And input and access pattern was also leaked in the PCPP proof. So one idea, the main issue is actually the leakage of this projected message coordinates. So one idea is to make use of oblivious RAM. But unfortunately, oblivious RAM requires to perform physical reads and writes even for read-only operations. So then we have to tackle this question of updatability in projection codes. So now let us see whether projection codes can support updates. So what you do when you have an update, you end up updating the entire code word. So if you make use of projection codes, then the online prover time would be proportional to the size of the database, and we are again back to square one. So then we need to see that can we come up with the notion of projection codes which provides updatability feature in a sublinear time. Now this conflicts with the notion of robustness guarantee of any encoding scheme, because if two code words differ, two messages differ by 1 bit, then there is going to be delta and fraction in which they would differ. So then we need to consider a relaxed notion of robustness, and a similar issue was encountered in TCC 14 work during the construction of locally updatable and locally decodable codes. So with this, we come up with this notion of locally updatable projection codes. So let me define what these are. It comprises of 4 algorithms. 3 algorithms are same as the previously defined for projection codes. The update algorithm is something that is new. Update algorithm takes as input a sequence of updates of length n, and it updates as sublinear bits of the code word x. This is the goal, like this is what we would want to achieve. And the robustness guarantee of the update algorithm is that if x is delta close to a code word y, then x prime, which is the output of the update algorithm, that x prime should be delta close to z, where y is an encoding of message small y, and z is the encoding of message small z, where z is the updated message from from the starting message y. Now, projection algorithm, the first guarantee that we have is same as that was there in the projection codes algorithm. That is, if the projected code word is robust, then you should be able to decode and obtain the projected message. The second requirement is that if you have a code word which is corrupt at certain location, but it is still delta close to a valid code word x, then decoding this corrupt code word at the projected code word locations, you should be able to get the projected message. So with this defined, let me define the notion of buffered Hamming distance, which we recall from the TCC work. This is the relaxed robust notion of robustness that works for our construction as well. So here we'll view the code word to be split into buffers, log and many such buffers. The first buffer is of length 1, second buffer is of length 2, and so on. The buffer's length increase exponentially. Then 2 code words are said to be having a buffer distance of less than delta n if each of the corresponding buffers have a distance of less than delta n fraction, and this distance corresponds to the Hamming distance at the buffer level. Then we say that these 2 code words have a buffer Hamming distance less than delta n. Now, coming to our LUPC construction, of course, we do not have time to discuss the construction in its full detail, but the main takeaway from this construction is that we are going to combine the hierarchical ORM data structure with projection codes. So first, the encoding algorithm is same as the projection encoding algorithm. So you just encode the message X using the projection encoding. Now for the update algorithm, what you do is that the global code word resides at the last level of the hierarchical ORM, and you organize this updates in the same structure as that is there in the hierarchical ORM construction. And you encode each of these levels using projection encoding. So now when you want to apply and obtain a projection, what you do is that you first consider the update entries in the plain text. Then you determine, given a sequence of message coordinates S1 to Sk, you determine the update entries corresponding to index S1 in each level of the hierarchical ORM structure that we have here. And we determine this message coordinates. Then you do this for all the message coordinates that you want to project. So this way, you learn all these message coordinates, and then you apply the projection algorithm of the projection code in each of these levels at the encoding level. So now you consider each of these encoded levels, and you apply the projection algorithm, and you get the projected message. So now, we come to our ZK-RAM construction. So in our paper, we had actually abstracted out an information theoretic construction, and then we had presented by compiling it as a Killian argument. But here, I'll just give you a high-level idea of how different techniques combined in order to form our final construction. So in our ZK RAM construction, the high-level overview is as follows. So in the offline phase, prover will first apply the ORAM preprocessing and get the ORAM memory. And then it is going to apply the encoding of the locally updatable projection codes algorithm. Now consider that after many updates, this is the code word that you start with. And in this instance of online phase, you have a RAM program R and a witness W, with which you want to prove the execution on this committed database. So you consider the ORAM evaluation of this RAM program R. And this RAM program R, even though if the underlying RAM program is read-only, as we had seen that ORAM inherently performs write operations as well. So the dark green values, marked entries, denote the projection, and the yellow entries denote the updates that are made by the ORAM evaluation. So in the online phase, you generate a PCPP proof that proves consistency of projection, computation of the ORAM evaluation, and it proves that the code word has been consistently updated. Then you consider a secret sharing. We'll see what kind of secret sharing we need. Like for the time being, consider that we need a simple secret sharing. So you consider each of this encoded bits to be secret shared in the I-1th round. And in the ith round, the second set of entries here, these are the ones you obtain after the update algorithm. So here for all the entries which are unchanged, you consider the commitment from the previous round itself. For the updated entries, you consider the commitment from the current round. Then similarly, you generate a secret sharing of the PCPP proof as well. And you commit to this PCPP proof and the updated code words secret sharings in the online phase of the ith round. Now, the idea is we'll have the prover run the PCPP verifier in the MPC in the head approach. So for this, the receiver will receive randomness R from the verifier. And given this, a prover will then run PCPP in the MPC head approach and obtain this set of K-many views. And it commits to this views and sends it to the verifier. Verifier will open a fraction of these views and check whether it is consistent with the shares of the code word that had been committed in the ith-1th round and the updated code word in the ith round. And it will check whether the views of the verifier are consistent and whether in all the views you see that the verifier outputs 1. So once it performs all these checks, it is convinced and it accepts the proof. Now there is one issue that if verifier runs this algorithm multiple times without the secret sharings being updated, then it can eventually learn sufficient many shares which can help it reconstruct the entire database. So this is not secure, so whichever locations we end up accessing in the online phase, we need to update those shares, and that is why we use proactive secret sharing, and this is the final component in our puzzle, and this is our final construction. Now we have the following two open questions. So in our previous work, we had constructed a RAM in which the online time was scaling quasi-linear with the runtime of the RAM program, whereas in this case, it is quadratic. So can we construct a quasi-linear online proof time? And the second question is that our construction right now is stateful. So can we obtain stateless constructions even for the non-updatability case, updatable case? So these are the questions we don't know answers to. Yes, so that's it for the talk. Thank you. I'm open to your questions here.
Okay, we have time for one quick question.
Hi, I'll cheat and ask two quick questions. I think this is very nice work because we don't have much foundation for run programs, and this is great. You mentioned something about comparing with other works that don't use hash function in a black box way, and that was part of the motivation. My intuition is that some of these works, VRAM style, Pantry style, zero knowledge versions of those, could be more efficient concretely. Is it true? Do you have a comment to that? And how would you argue for pushing for black box constructions that make black box use of hash?
Yes, so for RGRAM constructions, the construction we had, the main overhead was the PCPP. So, and there are efforts that are being made to make PCPP more and more efficient in practice. But this construction right now requires MPC in the head approach. And that is why we have another factor of security parameter, multiplicative parameter. So it could be inefficient at the moment. And we are not sure how it compares to non-black box construction as of now. But yeah, it's interesting to see how they compare in practice.
Thanks.
Yeah.
Okay, let's thank speaker again. Our last speaker is Nella Braun, and he will talk about constructing no bandwidth volley-based ZK proofs for mixed arithmetics.
Okay, thanks for the intro. This is joint work with Amit, Carsten, and Peter. And I know the title is a bit long, but I will go through all the parts in the talk. Okay. So since this is not the first talk of the conference or the zero knowledge session, I don't have to introduce this. But in our case, we want the prover to prove knowledge of a witness W that satisfies a bunch of constraints. And in our case, we have a circuit that formalizes these constraints. And this can be a Boolean circuit made out of XOR or AND gates. And we can also consider an arithmetic circuit with multiplication and addition over a larger ring of field. Here we only consider fields. So both kinds of circuits have their own advantages and disadvantages. In a Boolean circuit, you have the bit representation of every bit, so you can just compare values bit by bit. However, in an arithmetic circuit, you have native addition and multiplication, and you don't have to do Boolean adder circuits, for example. So the natural idea is to combine both into a hybrid circuit, and then you use the representation for the part of your statement that is best suited for it. The way to do this is to introduce so-called conversion gates. In this case, it's an arithmetic to Boolean conversion, meaning it takes as input an element x over a large prime field, and we can then convert it to its bit decomposition over F2. We can also, of course, consider the other way around, giving a bit decomposition, reconstruct this value over Fp. And in contrast to MPC, in zero knowledge, the direction does not matter too much, because as we will see, the prover essentially commits to the inputs and the outputs, and then proves consistency of this bit decomposition. So the order's not that relevant. And if we have the bit decomposition, there are a bunch of other gadgets that we can prove more efficiently. For example, in fixed point arithmetic, after multiplication, you need to cut off the lower k bits. So if we have these gates, then we can just combine two of them and get rid of the lower bits. Other applications are extraction of the most significant bit or the sign bit, and this can also be used to, for example, compute this ReLU operation that is very popular in machine learning. Okay. So first I will give a short intro to voll-based zero knowledge. Then I'm going to talk about different approaches, how to prove conversions. And finally, I'm going to come to our approach using low-degree PRGs. Okay, let's start with voll-based zero knowledge proofs. First, where are we in the space of zero knowledge? Like for many people, zero knowledge is just snarks. So they have a very good proof size, but maybe at cost of a slightly larger prover runtime. And we are in a different setting where the runtime and the proof size are both linear, but especially for the vol zero knowledge proofs, the overhead compared to just a plain text evaluation of the circuit is quite low. So for every gate in the circuit, we only perform a few field operations. In general, this is designated verifier and interactive, But in many cases, we can also make it non-interactive and publicly verifiable with the vol in the head paradigm. And this also applies to part of our work. So what is vol? Vol is vector oblivious linear evaluation, and it's a two-party functionality between a prover and a verifier, or maybe in vol or OT terms, the sender and the receiver. So here I marked everything that the prover knows in blue and the verifier's value in green, so you can keep track of them. The prover inputs two vectors, the verifier inputs a scalar, and then obtains this linear relation between these vectors. In other words, the prover selects a line in some space, and the verifier obliviously queries at one point on this line without the prover knowing which point it was. Then if we choose a bunch of these values uniformly at random, then we get linearly homomorphic commitments. So we can look at every line of this correlation and see it as an information theoretic MAC on the value wi. And we can see that this gives us a commitment because it's hiding if we choose the values v uniformly random, then the QIs are random as well. And breaking binding, meaning finding a different wi and some other vi that satisfies the same equation, would imply guessing delta, and that can only be done with probability 1 over field size. So, meaning, in other words, finding a different line intersecting this first one in this unknown point delta. If the field is big enough, then we get a negligible soundness error. If it's small, we can do the same thing over an extension field. And let me just say that there are very efficient ways how to realize this functionality, for example, based on pseudorandom correlation generators. And this gives us a long vol correlation with very little communication. However, this value vector W is uniformly random. So it gives you random commitments. And if you want to commit a specific value, you have to send a correction. And that costs like, one field element of communication. Okay, so now we have commitments, meaning we can do commit and prove zero knowledge. The prover commits to all the circuit inputs, many intermediate values, and the output, and then it just argues that these are consistent with respect to the circuit function. And since we have linearly homomorphic commitments, this gives us already zero knowledge for linear functions. Commit to the input, compute the function on the commitments, open the output. So for general circuits, we also need a multiplication check, giving commitments to A, B, and C. We want to make sure that AB is equal to C. So the state of the art in this setting comes from works like line point zero knowledge and Quicksilver, and they had the following observation. Giving 3 such MAC equations, we can multiply and add them together to get a degree 2 polynomial looking like this. So here, the prover knows all the coefficients of this polynomial, so all the blue values, and the verifier knows delta, the evaluation point, and also, of course, the value at this point. And all of these can be computed locally by both parties. Now, if A, B, and C are actually a multiplication triple, then the first coefficient is 0, so we have a linear polynomial. And the prover then can prove correctness by just sending these 2 terms to the verifier. In practice, you would add some masking to ensure zero knowledge, and you can also batch many of such multiplication triples together to get like one proof. Now, we can view the MAC equation as, say, a degree 1 commitment, and this big equation there as like a degree 2 commitment to a value that is, in this case, C minus AB. But we can also generalize this to, okay, I forgot something. Soundness relies on, if there is an error, then the degree 2 value must be non-zero. So the prover basically has to find a polynomial that has a root at delta and, degree 2. So that happens only with probability 2 over field size because, P has degree 2 at most 2 roots. So finding such a polynomial would imply guessing delta, essentially. Okay, now to the generalization. So we can view this polynomial above as a degree 2 commitment to C minus AB, which in general doesn't have to be 0. But we can continue multiplying and adding such MAC equations together. And in particular, if we follow the instructions of a degree D circuit and apply these to degree 1 commitments, we get out a degree D commitment, which is again a polynomial in delta, where the output value of this circuit is the most significant coefficient. And then we can prove that this is 0 by sending a proof of size D field elements. So this circuit can be evaluated non-interactively, so both parties just have local computation, which of course increases with the degree. So you shouldn't do too high degree computation. And this will be important for later on. So let's talk about how we can convert a big field element to the bit decomposition. And why do we do this? We can just emulate F2 arithmetic in FP. So we commit to the bit decomposition, prove that it's correct. So we have to prove that these are actually bit. And then we can arithmetize Boolean operations. So AND is just multiplication, XOR is a bit more. However, it has the following drawbacks. Committing to the bits already costs us quadratic amount of communication, because for every bit we have to send a whole field element to perform this correction of the commitment. And moreover, XOR is no longer linear over FP, so it's no longer for free. So therefore we actually want to go to F2. And from the world of MPC, there are the following two approaches to check or compute in the MPC world conversion. So the first is based on doubly authenticated bits or doublets, which are just the same random bit authenticated or committed over both fields. And given such tuples, which we have again to create with quadratic amount of communication, we can very easily commit to X over both worlds consistency. So we send a correction, which is just using these doublets to mask our value. Then we perform some linear operations, and we have X in both worlds. So to reduce the amount of communication for creating these values, they have been extended to extended doublets, bits, where R is now a field element, and the second part of the tuple is its bit decomposition. Creation is much cheaper. You only need to send m bits to create an adder bit, but you need to create a few of them to employ a cut and choose consistency check. But it's still much less than the m squared term from before. So the correction is now the same as before, just in an arithmetic world, but that also means we have to prove a Boolean addition circuit over F2 to remove the mask again. And to get like the smallest bucket size B of 3, we have to prove large batches of conversions, say, I don't know, 2 to the 20 or so. But this was like the previous state of the art, which we did in these works up in Debris and simultaneously some other people in Mystique. So we ask ourselves, can we create doublets which have this nice way of using them with low communication compared to the previous approach? So we used PRGs to obtain this result. And the high-level overview is we first commit to a short seed. So we commit to L doublets. We prove that they're consistent. We are paying the full cost, but it's only a one-time cost. In the next step, we non-interactively apply the low-degree PRG using this higher-degree Quicksilver to obtain commitments to the output of the PRG, but these commitments are now of higher degree. Then we can use them very similarly as before, just we have to make sure to use like degree D2 or DP constraints in Quicksilver to prove our conversions and other gadgets. And if we want to have more, then we can use part of the output to reseed the PRG again. So how does the PRG look like? We use either sparse LPN, which I won't talk about in this presentation, or we use Goldreich-style random local PRGs. So in a k-local PRG, each bit of the output can be computed as applying a public predicate to a random selection of k bits of the seed. So one predicate could be TSPA, three-sum and paired AND, which we can see is like a very simple Boolean formula of degree 2 over F2, but it can also be computed very efficiently as a degree 3 polynomial over a larger field Fp. And a different predicate would be the XOR majority, which gives us a better stretch, but at the cost of having a more complex predicate. So here we can show that the degree over F2 is at most 7, and over Fp is at most 11. So the degrees and the computation cost increase if we apply this predicate. So what we do is we just take the commitments to our seeds, we non-interactively apply this predicate, and we get the dar bits as output without talking. So to come to an end, we implemented our Goldreich PLG-based protocols in the Swanky framework by Galois, and we did some comparison with prior work, in particular the A to B protocols. So if we have an interactive proof system over this mersenne prime field with modulo 2 to the 61 minus 1, then we can see that for small batches of conversions, say 2 to the 10, we get an improvement of 2 to 3 times, both in runtime and in communication. For a larger set, here we see that A to B becomes more efficient. We have a bit worse runtime in a fast network, but roughly the same in over the internet. But communication drops like 10 times. We also implemented fixed point arithmetic and benchmarked that, and we see like a much higher improvement here, because in our case, we don't have to connect like 2 conversion gates, but we essentially pay half of 1 conversion in our way, because we don't care about the F2 part at all. We can just commit to a bit over commit to a seed over Fp, apply the PLG over Fp, and then use these bits over Fp to prove the fixed point truncation. This is because we don't need the output in the F2 world. So we also see an improvement in runtime here and communication as well. And moreover, if we, for example, take the XOR majority predicate, then we pay amortize roughly 0 volts per conversion. So the number of calls to this initial functionality, or like the size of its output, is much, much smaller compared to prior work. And this is really great if we want to have vol in the head proofs, because here we cannot use like standard LPN-based PCGs to create this vol correlation, but we have to pay more. And we estimate that with like a 128-bit field, we get an improvement in proof size of about 20 to 150, depending on parameters. Okay, to summarize, vol-based zero-knowledge proofs are like lightweight, fast, linear size, and we can make them non-interactive in many cases using vol in the head. And our approach gives us conversions between Boolean and arithmetic circuits that use way less communication than before, and also much less vols, which is like good for vol in the head. So we have these two instantiations from sparse LPN and Goldreich PLGs, and we use them to like prove a range of gadgets. So one open question that I want to conclude with is, how can we commit to even fewer bits over a large field? Because here it's more efficient than previous work, but we still have to commit to the seed before. And say we need less dar bits than the seed size, then of course it doesn't make sense to first commit to seed, expand, just to use a few bits. So I don't know, I would like to have a better way to generate fewer bits than before. Okay, thanks, that's it.
Are there any questions? If not, I have a question. So you mentioned you can easily support vol in the head and the public verifiability. Like what's the intuition why it's so easy to extend for public verifiability?
So, I mean, vol in the head basically gives you a non-interactive, okay, gives you a way where, okay, let's start differently. So in vol, the observation for vol in the head was that this value delta, which is in the interactive case, it's like the secret state of the verifier, which is the reason why it's designated verifier and not public coin. But once the prover has done its work, it doesn't need to be secret anymore. So at the end, it can be revealed. And the idea behind the vote in the head is that you get like a slightly different functionality, where first the prover commits to its input, and later the verifier chooses a delta, which then the prover is allowed to learn, and obtains its part of the output. So the prover can already use its part of the correlation to do the proof, and later on the verifier can choose the delta.
So basically, this mechanical conversion doesn't affect this kind of property, so you can easily do the conversion do the default in the head setting.
Yeah, as long as you don't need any secret state. So we have also the sparse LPN-based variant that I talked about, and that's not compatible, but the Goldreich GG1 variant is.
Okay, yeah, thank you. Let's thank the speaker again, and thanks everyone for coming, and this is the end of the session.